Okay, so welcome back to class today. Um, the plan for today is just to continue on with systems of linear equations, which we started last time. And we should make it a decent bit of the way through this material today. We're just kind of, lumping all of this into kind of one big discussion. Note that the Unit 1 exam is this week. It's on chapters 1 through 3, focusing on chapters 2 and 3. The sample exam is available. It was available last week. And just a quick reminder, no Proctor U for this first exam. We're just working out a couple of tech details, but plan to have that up and running for the second exam. And as I mentioned, don't wait until the last minute to take the exam. The exam isn't due until Sunday at 11:59 p.m., but I would strongly recommend that you plan to take it on or before Thursday night. That way, if anything goes wrong, you have one full business day plus a couple weekend days for working out a solution, whatever that may look like. If it's a tech issue or power outage or a life issue or something, give yourself a little bit of buffer there. So I think that's all I have to say on that note. Are there any quick questions before we get started? Okay, so solving linear systems in two variables. So recall that there are two basic methods for solving linear equations, algebraic and graphical. And if we have a system of two equations and two unknowns, we can think of each of these equations as a line on a graph or a line in the 2D plane. And we're thinking of a solution as an ordered pair x comma y that simultaneously solves both of these equations algebraically, or graphically what that means is it's a point that is simultaneously on both lines. So graphically speaking, we're looking for the intersection of two lines. Now we saw that's probably not the most efficient way to solve most problems most of the time if we're looking for an algebraic solution. But this perspective does help us understand some of the edge cases. Like, for instance, if we have two parallel lines, if the first equation and the second equation graphed turn out to be two parallel lines that are not the same line, we'd have no solution. If they turn out to be lines that intersect, we'd have one solution. Or I suppose it's possible they could just be the same line. So parallel lines that are exactly the same, x plus y equals 1 and 2x plus y equals 2. That's just the same line. So I have like line 1 there and line 2 right on top of it. Well, now every point on either of these lines is also on the other line. We have infinitely many solutions. So these are our three possible scenarios. So we're looking for intersections between lines when we're speaking graphically, or when we're speaking algebraically. What we're usually trying to do is to take two equations and two unknowns and get it down to one equation and one unknown. Ax plus b equals c, something like that. And then we can just solve that linear equation, get x equals number, and then plug that into one of our original equations, for instance, to get y equals number and get our unique solution that way. Or perhaps things don't, work so clearly as this, and we end up in one of the other special cases. And we'll see a couple more of those today. We saw one of those last time already. So that was a quick recap of the solution methods that we'll be applying today. And just recall that the substitution method, the idea is to solve one of our equations for one of the variables and then substitute into the other equation. The addition elimination method, the idea is that if we have two equations, we can add those equations together. We can add the left sides together and add the right sides together. That's perfectly valid. That gives us a new valid equation. Most of the time, that's not super helpful right off the bat. But when used in conjunction with the fact that we can multiply either or both equation by some number on both sides, and that also results in a valid equation, we can set things up so that if we multiply the first equation by a certain number and the second equation by maybe a different number, and then we add them together, maybe one of our variables drops out and we're left with one equation and one unknown. So those were our two algebraic solution methods. Okay, so let's take a look at this. This is a problem that we worked through last time. We saw how much cooking vinegar, which is 5% acid by volume, and how much cleaning vinegar, which is 7% acid by volume, we needed to combine to make 30 fluid ounces of a solution that's 6.2% acidity. And that made sense because 6.2% is between 5 and 7%. So it kind of makes sense that we should be able to reach that acidity. As kind of a side note, you might look at this and say, like, why is cleaning vinegar only like, quote, 2% stronger than cooking vinegar? Note that it's actually quite a bit stronger. It's 2 percentage points stronger, but on a scale of 5 percentage points. So it's actually like 40% more acidic, the cleaning vinegar than the cooking vinegar. So be a little bit careful when you think about percent change versus percentage point change. There's only a 2 percentage point increase, but going from 5% to 7% acidity is actually a 40% increase in acidity for those 2 percentage points on a scale of 5 percentage points. So these are, actually fairly different acidities. So the question now is, can we make an 8% solution? Now, I suppose if we had, if we had access to two fluids, one of which was, say, glacial acetic acid, there's just 100% vinegar, which you need to be very, very careful with when handling. Maybe not very, very careful, but you want to be careful when handling it. And like water, which is 0% acidity, well, then we could probably make any acid we want, any acidity we want from 0 to 100%. But here we're desiring an 8% solution from two fluids which are 5 and 7% acidity. It seems like we shouldn't be able to come up with an answer here. What's going to happen? Are we going to like suddenly fall into one of these edge cases or something? Where is the no solution going to come from? Let's investigate this. This was an exercise from last time, and we're going to work through this one today just to get us started. Okay, so what can I do? Maybe I'll do substitution here, mainly because I look at this first equation and I see that it's going to be easy to solve for one of the variables in terms of the other. So let's say that A is 30 minus B, right? Whatever amount of cooking vinegar I use is going to have to be 30 minus the amount of cleaning vinegar so that the two combined make a total of 30 fluid ounces. So A is 30 minus B, and I plug that in for A over here. So I mean, not the prettiest equation in the world, but I do have one equation and one variable. And I know how to solve a single linear equation in one variable. I simplify both sides, combine all like terms to get number times variable equals number on both sides. And then I go through my equation solving steps, isolate the variable term, isolate the variable itself, and then check. So if I multiply out, I get 0.05 times 30 minus 0.05b plus 0.07b equals 0.08 times 30, or this gives me 0.02b plus 0.05 times 30 equals 0.08 times 30. Okay, so now what do I end up with? I want to isolate my variable term. I want to isolate 0.02b, so I subtract 0.05 times 30 from both sides. Sorry, my allergies have been really acting up. 0.02b equals, and then I have 0.08 times 30 minus 0.05 times 30, that's 0.03 times 30. And what do I end up with? I end up with the b has to be what? 0.03 over 0.02 times 30. Well, that's just 3/2 of 30. I mean, I guess this seems pretty reasonable. We just give b equals number. But the issue is, what's 3/2 of 30? It's 45 fluid ounces. So we're looking at this and we're saying, wait, I need to make a 30-ounce solution, but somehow I end up with 45 ounces of cleaning vinegar that I have to use. That doesn't really make sense. And it makes even less sense when I plug back in and I get A is 30 minus B. Or A is 30 minus 45, or negative 15 fluid ounces of cooking vinegar. Is this a mathematical solution? Negative 15 comma 45, is that a point of intersection on the 2D plane where these two lines cross? Sure. Does it solve the application problem? No, because I pretty clearly cannot combine a negative volume of vinegar with a bigger volume of vinegar and like somehow have the two like cancel out down to 30 fluid ounces. So my application requires A bigger than or equal to 0 and B bigger than or equal to 0. So this is not a real solution to my application, even though it is a mathematical solution to this 2x2 system. Any questions on this? Okay, so let's take a look at this system. So we could probably use addition elimination method or substitution method here. And as I think I mentioned last time, that as we go through, we're going to pick, one method to use for each of these. I'll switch back and forth between methods. But it's good practice when you're going through to maybe try the other method, right? So if we use addition method here, maybe try doing this one with substitution, or we used substitution on the last one, try doing it with addition. But I see that this is set up pretty nicely to use the addition method. And I can just, if I add these two together right away, what do I get? I get 3x minus 2y equals 10. That doesn't quite get me what I want. And the problem is that minus y plus minus y, they don't go away when I add them together. But I'm like almost there, right? I could think of subtracting instead of adding. That would be mathematically valid. But if we try to just subtract in our heads, that's pretty error prone. So let's go through and let's multiply equation 1 by -1. In other words, I get negative x plus y equals -2. Just multiplying each term by -1, flipping the sign on each term. And then equation 2 can just come down. If I can write 2, equation 2 can just come down. I didn't change that one at all. Now I add them together, what happens? Negative x plus 2x is x, plus y minus y. My y's completely go away. 8 minus 2 is 6. And actually, I get my x coordinate of the solution right away. I actually don't even have to do anything else here. So I see that x equals 6 is the x component of my solution. How do I get the y component? Well, I go back to either of my two original equations and plug in x equals 6. So maybe I'll take equation 1, and I get 6 minus y equals 2. I add y to both sides, I subtract 2 off of both sides, and I get y equals 4. Then I can go back and check, is it true that 6 minus 4 equals 2? Yeah, so equation 1 is satisfied. Is it true that 2 times 6 minus 4 is 8? Yeah, 2 times 6 is 12, minus 4 is indeed 8. So equation 2 is also satisfied. This does represent a solution. So we found a solution for this system. Okay, now looking at this example, 3x plus 4y equals 8, negative 6 minus 8y equals negative 16. What do we end up with here? I'm actually going to do this one both ways. I think we'll see why in just a minute. I'm going to do it both ways. For the addition elimination method, maybe I decide that I want to eliminate the x's. I want to end up with one equation and one variable, with that variable being y. I want to get rid of the x's. I see if I just added now, I get 3x minus 6x. That's not going to make the x's go away. But if I multiplied the first equation by 2, I get 6x from the first equation. And then when the second equation came down, I get negative 6x. I see those are going to go away now. I've made my x terms, the coefficients, match with opposite signs. So when I add them together, the x's are going to go away and presumably leave me with y's. But let's make sure that we do the rest of the work carefully. So I multiply equation 1 by 2. So 3x multiplies by 2 to 6x plus 8y equals 16. And then equation 2 just comes down, minus 8y equals negative 16. And I add these together, and my x's go away. But I actually noticed that my y's go away as well. 8y minus 8y is 0. And I actually noticed that my constant, 16 minus 16, go away as well. 0 equals 0. So my question is something like, what values of x and y can I plug in to get a true statement here? Well, I almost want to say I can plug in any combination of x and y to get a true statement, because 0 always equals 0. But that would be a little bit too loose, a little bit too free. If we think a little bit more abstractly, like kind of my goal here was maybe to eliminate the x's. So really what I'm kind of saying here, this is really a 1-by-1 equation is how we really want to think about it. And let's say, for instance, the variable y. We could also think of it as being in the variable x, but it's really a 1-by-1 equation, not a 2-by-2 equation somehow. It's a 1-by-1 equation in y. So really we can choose y any way we want. However, once we choose y, we are definitely still constrained, right? I still need 3x plus 4y equals 8, and negative 6 minus 8y equals negative 16. It turns out that what we would normally have as two distinct constraints here just ends up being the same constraint, but I still do have one constraint to meet. So I can choose y freely, but once I choose y, x is determined. Or I could choose x freely, but once I choose x, y is determined. So maybe I say something like y can be any real number, and then once I pick y, x has to be what? something like 8 minus 4y over 3. Or I might just say infinitely many solutions. So this is one of our edge cases. This is the geometric case where we have two parallel lines that happen to be exactly the same line. Sorry, give me just a second here. Okay. Swear I must be like allergic to teaching math or something. It seems like as soon as I start my classes for the day is when my allergies kick in. Uh, okay, so we saw that when we do the addition elimination method, and instead of eliminating one variable, we kind of eliminate everything. We eliminate all of our variables. That's when we're in one of these edge cases. What does this look like in substitution? Well, let's solve equation 1. I guess maybe I'll solve it for y. So I have 4y equals 8 minus 3x, or y equals 2 minus 3/4 x. So just rearranging equation 1 a bit, this is what I get. This is an equation that is equivalent to that original equation 1. I can now plug this into equation 2. What does equation 2 say? It says negative 6x minus 8y equals negative 16, and I plug my value for y in terms of x in for that y. And now I've reduced to, again, one equation and one unknown. It's a little clearer now that I've reduced to a 1 by 1 than it was over here. What are the solutions x to this 1 by 1 equation? Well, I start by distributing. And minus 8 times minus 3/4 is plus 8 over 4 is 2 times 3 is 6. And I see I just get the claim negative 16 equals negative 16, which is true for all choices of x. So I could think of, x as being a free variable. X is just some real number, but once I've determined what x is, once I decide what x is, if I say pick x equals 1, then I do have a constraint on y. Y has to be 2 minus 3/4 x. So if I pick x equals 1, y has to be 2 minus 3/4. So if I end up with a resulting 1 by 1 equation where all my variables drop out and the ending statement is true, then I have this situation of infinitely many solutions where one of my variables I can think of as being free, they can be any real number, and the other variable will be constrained by the common constraint from these two equations. Okay, a system like this, we saw that substitution was a bit messier here than the elimination method. But here, this is set up very nicely for substitution. Y equals 1/2 x, I'm ready to just plug in. I've already got y solved solved in terms of x. And if I have negative 2x plus 4 times a half x, negative 2x plus 2x is 0 equals 7. This is always false. No matter which value of x I pick, this will never be a true statement that 0 equals 7. So this is no solutions. If I wanted to force the issue, I could do addition and elimination method here. Again, it's probably not the best method to use for this situation, but because it's one of these special cases, I want to show what it would look like. So maybe I can make this something like multiply by 2, and then subtract y. So like x minus 2y equals 0. So just taking y equals 1/2 x, multiplying both sides by 2, and then subtracting the 2y. So I just rearranged equation 2 to make it look more amenable to the addition elimination method. And again, maybe I decide that I want to eliminate the x's. So I see right now, if I add the two equations together, I get negative 2x plus 1x. They don't cancel out. But if I took equation 2 and multiplied it by 2, I would get negative 2x plus 2x, and they would cancel out then. I'll just copy equation 1 down as is. We're not changing that one. Equation 2, I'm going to multiply it by 2 everywhere. So I have 2x minus 4y equals 2 times 0 is 0. And I add, my x's go away, which is great. My y's also go away and give me 0 equals 7. Again, my goal here was to eliminate x's and get a 1-by-1 equation in y, for instance. You could have also imagined doing this, eliminating the y's and getting an equation in x's that would be the same math. But if I'm thinking of this as a 1-by-1 equation in y, what value of y can I choose to make 0 equal 7? There's no choice for y that will ever make 0 equal 7, so this is always a false equation. There's no value of y that makes this equation true, and then there's no ordered pair x comma y that makes this true. This is the geometric or graphical situation where we have two parallel lines that are not the same line. Right, we can see that these have the same slope, but they have different y-intercepts. Any questions so far? Okay, so let's look at some application problems. So here, Bob is packing his lunch consisting of grilled chicken and steamed white rice. So pretty healthy meal, it seems like. He plans to eat 4 meals today with like a total daily calorie intake of 2,200 calories and a total protein intake of 140 grams of protein spread evenly over the 4 meals. And Bob looks up either on the back of his package or online. Grilled chicken, it has 67 calories per ounce and 5.3 grams of protein per ounce. Steamed white rice has 37 calories per ounce and 0.8 grams of protein per ounce. How many grams of chicken and how many ounces of rice should Bob pack for lunch? Okay, so let's set up two variables. So C is going to be the number ounces of chicken. And R the number of ounces of rice. And we'll have one equation for the calories per meal and another equation for the protein per meal. So the calories for this meal, he wants the total to be 2,200 calories over 4 meals. So 2,200 over 4, that's 1,100 over 2. I think that's 550 calories per meal. And how does he get calories? He gets them from chicken or rice. So grilled chicken has 67 calories per ounce. So that's 67 times the number of ounces of chicken. That's the number of calories coming from the chicken. And the rice has 37 calories per ounce, so plus 37R, and that's equal to 550. And then for the protein, again, he wants 140 grams of protein spread evenly over the 4 meals. So 140 over 4 is 70 over 2, or 35 grams of protein that he wants for this meal. How many grams of protein come from 1 ounce of chicken? Well, 5.3. About 5.3C plus what? Um, and then rice has 0.8, 0.8R. Now, of course, we have a practical constraint that C and R have to be, well, I guess, bigger than or equal to 0. So when we work through and get a mathematical solution, I mean, maybe the math suggests that he needs, negative 4 ounces of chicken or something. Well, that's not a practical solution. There would be no solution in that case. Maybe the chicken and rice meal choice, along with the calorie and protein constraints, just don't work in a practical sense. So that's a possibility. It's also a possibility that we get, something like infinitely many solutions or no solution. We could mathematically not get a solution. We could practically not get a solution, or we could practically get a solution, practically and mathematically. So let's work through this one. Again, a couple different ways we could solve this. I think probably the first thing I want to do is get rid of these decimals. So I'm going to leave the first equation alone. But the second equation, I'm just going to multiply by 10 on both sides. Now you might say, well, wait, doesn't this mean that he's going to get 350 grams of protein now? Well, no, we just multiplied everything by 10. This is going to have the same solution set as the original two equations. We've just massaged it into a form that's a little easier for us to work with mathematically. So these two constraints, these two equations, are tied directly to the original question. But here we've just done some mathematical manipulations to make the thing a little easier to solve. Okay, I've got a couple of different ways to approach this now. I could either use addition elimination method, but what do I have to do for that? Let's say I want the C's to cancel out. Well, I need to multiply equation 1 by like negative 53 in all the terms, and equation 2 by 67 on all the terms. And then I have like negative 53 times 67 times C and positive 53 times 67 times C. They would cancel out, but those are kind of really annoying numbers to multiply by. I'm going to end up with really big numbers at the end. I think maybe I'll just bite the bullet and do substitution here. So I'll take equation 1, solve it for, say, maybe C. So it's 550 minus 37R over 67. Solving that equation for C, and then I'll plug that in equation 2. So equation 2, 53C, 53 times 550 minus 37R over 67 plus 80R equals 350. Okay. Now, what could I do here? I guess I could multiply everything by 67 if I wanted to. Um, that probably wouldn't be all that much different than the addition elimination method. Um, I could go a couple different ways here. Maybe I will do that. So I could do this, and I would actually get something pretty similar to if I did the addition elimination method. So did I really save, a whole lot of time and effort going one direction or the other? Probably not, unless I'm in a case like, say, this one where like I already very clearly have one equation solved nicely in terms of the other, or one equation solved nicely for one variable in terms of the other. So is it really like that much of a huge benefit to always go one direction or the other? I don't think so, but sometimes it's just a little easier to get started one way or the other. Okay, so what do I have then? My coefficient of R is 80 times 67 minus 53 times 37 times R. And then I would have plus 53 times 550. Let me subtract that over. And I'll just do this off screen. Bring up the calculator. The calculator is not wanting to work. I was doing this before the semester and I got it fixed early in the semester and now it's not working again. Okay, then I will use my phone, I suppose, for this. So what do I need? I need 80 times 67 and then minus parentheses 53 times 37. So this gives me 3399 R equals, and I have 350 times 67, 2000 or 23,450, and then minus 53 times 550. I think I did that. Let me do that again. 350 times 67 minus 53 times 550. I ended up with a negative number here, and I don't think I should have. Did I mess something up? I should break out my TI-83, but I'm not 100% sure where it is right now. This is why I recommend a graphing calculator, but mine does not seem to be wanting to work at the moment. I did have yesterday, things were being very crashy on me. Um, but anyway, at this point, we have one equation and one unknown, and I think we should be able to solve for it. And I thought that this had a reasonable solution, but I was coming up with a negative number as the solution, and I don't think that's right. So I will get the graphic calculator up and working, which will probably just restart the computer and it'll end up working again. But obviously, I don't want to do that in the middle of lecture. So to be continued for this one. But anyway, this is how we would set up the system and work through the solution. And if we had a calculator that was cooperating, we would get the solution this way. But we'll revisit this one next time. I'll type it up and we'll wrap it up when I have the TI-83 working a little bit more reliably. Okay. Okay, so next application. The Jones family took a 24-mile canoe ride down the Indian River in 3 hours. After lunch, the return trip back up the river took 6 hours. Find the rate in miles per hour of the canoe in still water and the rate of the current. So what's kind of the idea? We have a river here, and we're thinking that there's a current generally kind of going this direction, let's say. And I know the ride, quote, down the river took 3 hours, and the ride back took 6 hours. So the canoe was going, had kind of a faster relative land speed going on the first part than the second part. So the canoe started here at, say, time 0, traveled this 24 miles, and it took 3 hours to do that. And then coming back the other direction took 6 more hours. And we'll assume that the canoe has a speed c, so that if you were sitting on a still lake, let's say, and you were paddling the canoe, you would be going a certain speed. But rivers have movement, so there's a unfortunately, current also starts with c, so let's call that the speed of the river. In other words, the current, and we'll call that r. So we, interestingly have the same two variables as our previous example, c and r, but here they stand for canoe speed and river speed rather than chicken and rice. Now, what do I know? I know that I've covered a distance of 24 miles in both cases. And I know the distance is rate times time. Or in other words, speed times time. So distance 1, 24 miles. The first leg going left to right, when the canoe speed is being added to the river speed, this is rate or canoe speed plus river speed. The current is pushing us in the same direction we're paddling, times time, say T1, or this is C plus R, and that took 3 hours. So we have one equation, 24 equals C plus R times 3, or that's 3C plus 3R. And then for the return trip, we do something similar. Let's do that maybe in green. Distance 2, the return trip, well, that happens to be the same distance, still 24 miles. And that's rate times time. But now we have the canoe speed minus the current, minus the river speed. We're fighting against the current. And in that case, it took 6 hours. Or I have that 24 equals 6C minus 6R. So these are my two equations, the two unknowns. I know that practically speaking, my canoe speed has to be greater than the current, right? If the current was 10 miles an hour and my canoe speed was like 5 miles an hour, when I'm fighting against the current, I would never get back to where I started. So I know that the canoe speed has to be bigger than the river speed. That's just kind of a reasonability check that I can keep in mind. And let me look at my two equations. So what do I have? I have 3C plus 3R equals 24, and 6C minus 6R equals 24. I think probably addition elimination is going to work well here because things seem to be lining up pretty nicely. The 3s versus the 6s, just the factor of 2 off. I could multiply equation 1 by 2 and get 6c plus 6r equals 48. But I could actually multiply equation 2 by 1/2. Maybe I'll go that route just to keep the numbers smaller. Three c plus 3r equals 24. And then I multiply equation 2 by 1/2, I get 3c minus 3r. I think I've switched from using big C and big R to small c and small r, but not a big deal. And then I have to divide my 24 by 2 as well to get 12. If I add these together, I get 6c. My r's go away, equals 36. Or c equals 6. And my units are miles per hour, right? I traveled a certain number of miles in a certain number of hours. So I get that my canoe speed is 6 miles per hour in still water. And then I come back up here, maybe I take equation 1, for instance, with c equals 6. 3 times 6 plus 3r equals 24. Or I have 24 minus 18 is 6, so 3r equals 6. Or the river speed, the current is 2, and that's 2 miles per hour. I do see that my canoe speed is bigger than the current, so that makes sense from a reasonability standpoint that I can paddle faster than the current can push me downstream, so I'm able to get back to the beginning. So that that reasonability check kind of checks out. Okay, any questions on anything so far? Okay, so next example. So we have a situation where the sum of two numbers is 12, and one number is 7 less than the other. Find the numbers. A little more of an abstract example, so not a whole lot to go on here. But if I just call these two numbers, say x and y, on one hand, I know their sum is 12. And on the other hand, one is 7 less than the other. I mean, when we're talking about the sum, things are commutative, that everything is nice and symmetric. One number is 7 less than the other. Does it matter which one I pick to be 7 less than the other one? Does it matter whether, x is the bigger number or y is the bigger number? Well, no, it doesn't seem like it, right? Up here, it was important that I, get things the right way, that I get my signs and so on for C and R correct. If I had set up, 24 equals 6R minus 6C, well, that wouldn't have been correct, because C specifically represents the speed of the canoe in still water. It's a specific thing. But here we just have two numbers. So I can just pick whichever one I want to be bigger. One is 7 less than the other. So let's let y be 7 less than x. Y equals x minus 7. If you picked x equals 7 minus x equals y minus 7, no problem. And here it looks like this is set up nicely for substitution. That we have x plus x minus 7 equals 12. 2x minus 7 equals 12. Or x is 19 over 2. That's the x value. And we want to find both numbers. So then what's y? X plus y equals 12, or I suppose y equals x minus 7. Y equals 19 halves minus 7, or minus 14 halves. Y equals 5 halves. So their sum, 24 over 2 is 12, and one is 7 less than the other. They are 14 halves apart in size. Questions so far? Okay, let's look at this application then. Tickets for the community fair cost $12 for adults and $5 for children. Don't know why I said dollars there effectively twice. On the first day of the fair, 313 tickets were sold for a total of $2,181. How many adult tickets and how many child tickets were sold? So let's set up our two variables, A for the number of adult tickets sold, C for the number of child tickets sold. And what do we know? We know the total number of tickets sold was 313. So A plus C is 313. We also know the total revenue, $2,181. Each adult ticket sold brought in $12. So the total revenue from adult tickets is 12A. And each child ticket sold brought in $5 of revenue. So the revenue from child tickets sold was 5C. And that's got a total 2181. And here maybe we'll do the addition elimination method. So we'll multiply equation 1. And let's try to eliminate C maybe because we have to multiply by a smaller number to make that happen. So I'll multiply equation 1 by -5. So I have -5C plus 5C. The C's will go away, the A's won't, and I'll be able to solve for it for the A's. So I have -5A minus 5C equals, and it's easy to forget to multiply on the right-hand side, but let's not forget that, equals -5 times 313. Equation 2 just copies down. And then I add them together. I see minus 5C plus 5C, my C's go away. 12A minus 5A is 7A. And this is 2181 minus 5 times 313 on the right-hand side. And let's do this. And that gives me 616 equals 7A. And this tells me the number of adult tickets is 616 over 7, which is 88. So we sold 88 adult tickets. And then we can come up here and equation 1 seems like the easiest one to use. Plug 88 into equation 1. 88 plus C equals 313. And C equals 313 minus 88, or 225. So it looks like we sold 88 adult tickets, 225 child tickets, for a total of 313 tickets sold and a total revenue of $2,181. So any questions on any of the material from today? Okay, when we come back, we'll do another example or two. We'll move on to 3x3 systems, talk about that a little bit, not a ton, and I'll figure out what's going on with this chicken and rice example here. If I either did an algebra flub somewhere, or most likely I just typed it into the calculator wrong, and when I get the graphing calculator back up and running, that should be that should proceed much better.